think we are recording. We'll see. All right, well, we're continuing on in our section on sampling distributions. And on Monday we left off and we said that the sampling distribution is the distribution of all the possible values for a sample statistic. The example that we used was, imagine that we've got a population of Reese's Pieces candies in some giant tub. And we said if we continue to draw out samples of size 50 or whatever it might be, then we can observe different values of p hat, the sample proportion, every single time we take a scoop. And so what that means is that the sampling distribution in that case would be all of the different possible p hat values we might observe. Okay? So again, the sampling distribution, this is the distribution of all possible values of a sample statistic. Okay, such as p hat or x bar, such as p hat or x bar for samples of a given size drawn from the population. Okay, and so our example last time, we have a tub. This thing is filled with Reese's Pieces, and we said perhaps in the population exactly 30% are orange. So that means P being the population proportion, P is the population proportion, that is 0.3. And what we have is that if I draw a random sample from this population, then we might get different values of p hat. We want to know what is the distribution of the different values of p hat. We draw a random sample. Different values of p hat being the sample proportion. Okay, and what is the distribution of all of the p hat values we can see? Okay, and do you recall when we ran our simulation, we ran the simulation with the Reese's Pieces candy machine, do you recall what that resulting sampling distribution looked like? The resulting sampling distribution looked something like this. We had all of these lines. Something like that, and we said, well, you know what? It looks kind of like, if I can draw this, it looks kind of like the normal distribution. This is supposed to look unimodal and symmetric. Okay, so we said looks like. Okay, so is this conceptually okay so far? The idea of building up our sampling distribution, and I'm not giving a rigorous proof. I'm just saying, hey, it looks kind of like the normal distribution, and as far as this class goes, we're going to just say, okay, it looks normal. We're going to accept that it's normal. All right. And if you were to major in statistics, or you were to take a course in mathematical statistics or something, you would have to prove this, the fact that it looks like the normal distribution, not just it conveniently looks like the normal, and so we'll say it's normal. That's beyond the scope of our course. So we're just going to say, so this is something called the central limit theorem, and we're not going to try to prove it or anything. And, this is like a paraphrased version. The idea here is that the sampling distribution of p hat and also x bar can be approximated with a normal distribution. Okay, so we'll say the sampling distribution p hat and also x bar can be approximated with a normal distribution as long as certain conditions are met. And for the sampling distribution of p hat, can be approximated with a normal distribution with a certain mean, and so we'll say can be approximated with the mean equal to p. So the center of our sampling distribution is equal to the proportion in the population. All right, and I think that makes sense, right? So the center of the sampling distribution is the population proportion. Right, and I think that makes intuitive sense in that if the giant tub of Reese's Pieces is 30% orange, every time we take a scoop, we would expect to get a value close to 30% orange. Okay, of course, because it's a random sample, maybe it's higher or maybe it's lower than that. But in the long run, after many, many samples, we would expect them to be centered around 30%. Likewise, if we're taking a random sample of people, okay, and let's assume that in the world, I don't know, 51% of people in the world are female. Let's just say that, okay, and something around there. Every time we take a random sample of people, we would expect overall in the long run about 51%. Our samples to be centered around that proportion, 51% female, something around there. Okay, so I think that makes sense. Can be approximated with a normal distribution with mean equal to p. And the standard deviation, that's less intuitive, but and with mean equal to p and standard deviation equal to, and I'm just going to give you this formula. It's the square root of p times 1 minus p divided by n inside the square root. You might see something similar. I posted, I didn't cover this when we were talking about the binomial distribution, and I think it's okay. There is a quiz, there's a question on the quiz, but it's very straightforward, and it's going to ask you what's the standard deviation of a binomial distribution, and I've asked the TAs to put the formula up on the board, okay? And it's just going to be, it's the square root of n times p times 1 minus p. You're just going to, all it requires you to do is identify what n is and what p is in that binomial problem, then plug it in. This thing looks a lot like that, except in the binomial you have n in the, it's n times p times 1 minus p rather than p times 1 minus p divided by n. It's pretty much the same, except we're just dividing the count by n to get a proportion. But don't worry about this. This is going to be the property of the sampling distribution. So we are centered at p, and we have standard deviation p times 1 minus p over the square root of n. Okay? So let me do an example here. All right, so we will say in our rhesus pieces, we have P is equal to 30% orange in the population. And what we will do is we take random samples of 50 pieces. So we can say, what is the normal distribution we can use to approximate the sampling distribution? So again, we're just trying to approximate the sampling distribution. The exact sampling distribution is a little bit complicated, but we're saying, hey, we can approximate it with a normal distribution, okay? And so the normal distribution that approximates the sampling distribution, it's just a normal distribution where the mean is equal to p, 30%. And then the standard deviation is equal to the square root of p, 30% times 1 minus p divided by n, which is 50. So I come along and I plug this into my calculator. I get 0.3 times 1 minus 0.3, which is 0.7. Divide that by 50. And I take the square root of that, and I get a standard deviation of 0.0648. Throw in 1 for good measure there. Okay. And that's it. That's the normal distribution that will approximate our sampling distribution. And again, it's not exact. It's an approximation. But for our class, it's good enough. Okay. All right, and so with this in mind, we can then begin to answer questions about random samples that we draw. Okay, I'm going to flip the slide here. So we will say, so this is, we'll call this a sampling distribution problem. Right, and we'll say that the tub of candy, 0.30 orange, okay, and we will draw a random sample of 50 pieces. Same setup as before. Okay, and so we'll say, on the last slide we figured out what is the normal distribution that can be used to approximate it. Okay, so using that normal approximation, I'm gonna ask the question, approximately, I'll just say, so this is always gonna be kind of implied, approximately, what is the probability that a random sample of 50 pieces of candy has a p-hat of 0.4 or more. Z table. Okay. Well, we'll make a clicker question out of this. I've got to make up some answer choices here for you guys. And, don't have my Z table, so let's see. All right, so let me just do the math here. Okay, and so our choices are okay. All right. If you again, if you need to discuss with your neighbors, you're welcome to discuss with your neighbors. And I'll let the clicker run. Get the recording back going. Okay, and that is the correct answer. 88% of you got that correct. All right, so so yeah, the steps to do this, and I gave you a little bit of a hand by doing the last part for you guys, right? But the first part, okay, step 1 is figure out the normal distribution, okay? Now that was done for you. Figure out the normal distribution, but perhaps in future problems, it will not be given to you, right? So figure out the normal distribution. So you got normal, and we know that the mean is going to be equal to p, which in our case was 0.3, and we know that the standard deviation is the square root of p times 1 minus p divided by n. square root of 0.3 times 1 minus 0.3 divided by 50. And I keep clearing out my calculator. Okay, and this part was 0.06481. Okay, so this part you got to figure out. Now we did this on the previous slide, so I was hoping that makes it easier. And then step 2 is, solve like a normal problem. Normal being a normal distribution problem. I mean, I guess you could say it's a normal problem, but okay. But anyway, distribution. And let's see, go. Z is equal, and in this case, we want 0.4 minus the mean of 0.3, and then we divide by the standard deviation of 0.06481. And when I did this, I got a z-score of 1.54. Okay, and then we go to the normal table. We look up 1.54, and we find the area over here. Positive 1.54 is 0.9382. Therefore, this area over here is 1 minus 0.9382, 0.0618. Yeah. And it seems like most of you guys had that figured out. Is that good? So this is the sampling distribution. This is based on, this works because it's based on the central limit theorem. Right. And again, the central limit theorem, the loose paraphrase of the central limit theorem is that this sampling distribution of p hat can be approximated with a normal distribution. And then, I've given you the mean of the standard deviation. The real central limit theorem is a bit more complicated, but as far as this class goes, we just say, the part that's relevant to us is that that p hat can be approximated, sampling distribution p hat can be approximated with the normal distribution. Okay, and again, we will not try to prove that result. If you're curious about it, you can look up central limit theorem on Wikipedia, or you can take a course on mathematical statistics, and perhaps you will enjoy, I don't know, maybe that's your thing. Okay, maybe not. There was a little kind of an asterisk in the central limit theorem, and that is certain conditions must be true in order for us to use the central limit theorem. Okay, so that means not just because you're looking for a sampling distribution of p hat, or just because we're talking about p hat, doesn't necessarily mean that the central limit theorem works. There are 3 conditions we must check. Otherwise, we cannot approximate p hat using the normal distribution. Okay, so the following 3 conditions must be true . Otherwise, we cannot use the normal distribution to approximate the sampling distribution. Okay, so condition number 1 is that the sample, well, this is called the random and independent condition. Okay, and that states that the sample that we are looking at, the sample must be selected randomly. And individuals selected must be independent of each other. Okay. So basically, you want to make sure that the sample that we're dealing with, somewhere in the problem says it was randomly selected, and that there's no kind of biases that can form, right? So, you know, if we're going to try to estimate the proportion of Americans that, I don't know, subscribe to Netflix or something like that, when we conduct our survey, we have to select the people randomly. Okay, if we just you know, select our survey based on I don't know, some other criteria, like we contact people via an internet survey, that's not gonna work out, okay, because that's not gonna be random. Condition 2 is that we call this the large sample condition. Okay, basically the sample needs to be large enough. The sample must be, you know, quote unquote large enough. All right, and large enough is going to be defined as you must have at least 10 successes and at least 10 failures. You need in the sample. Okay, so the smallest sample you could possibly have is 20. Okay, and that's if you have exactly 10 successes and 10 failures. And chances are you're not going to have, if you have a sample of 20, you're not going to get exactly that. So generally, you need samples larger than 20, and you need at least 10 successes and 10 failures. So if the thing that you're looking for is quite rare, okay, you're going to need a very big sample to make sure you get at least 10 successes, right? So if you're saying, you know, what proportion of people have some, I don't know, you know, genetic chromosomal abnormality or something like that, okay, you know, probably you might survey 200 people and maybe only 2 people have that, okay? And in that case, that's not a big enough sample. You need to survey a lot more to make sure you have at least 10 successes. You need at least 10 people who say yes and at least 10 people who say no, okay? Sometimes the count is not given, and in those cases, you have to kind of estimate your count. Sometimes the count is not given, and so so figure out the count by doing n times p and n times 1 minus p. Okay, and that would give you kind of your number of successes and number of failures. Okay. So that's the large sample condition. You need at least 10 successes and 10 failures. And then condition 3 is the big population condition. And this means the population must be big compared to your sample, all right? Unless you're sampling with replacement. I got to throw that caveat in there, okay? So population, we'll say, must be at least 10 times bigger than the sample. Okay. Or you are sampling with replacement. Okay. So the idea here is that, you know, if you have a deck of cards, you know, you start off with 26 red cards and 26 black cards. Okay. You know, that first card you draw, you have a 50-50 or, you know, 50% probability that the card is black. Okay. Let's say that first card you draw is black, then technically what remains in the deck is 26 red and 25 black cards. Okay. And so it's no longer exactly 50% black for the second card you draw. And what we're saying is that if you're drawing less than 10% of the deck, then the changes that are brought about by taking out a card here and there, those changes are small enough that we can kind of ignore it. Okay? But once you draw out more than 10% of the population, then what you see in your sample begins to have an effect on the population. Okay, and so that's why we say the population needs to be at least 10 times bigger than the sample. Okay, when we're saying if you're drawing less than 10% of the population, the changes that happen, not that big of a deal. We don't have to worry about it. Okay, you don't have to worry about the big population condition if you sample with replacement, meaning if you draw out the card and you say, okay, I got a black card, but then I put it back in so that it remains 26 red and 26 black the whole time, then you don't have to worry about you know, taking samples that are too big. But if you're sampling without replacement, which is most of the time, then you want to make sure you're not drawing more than 10% of the population or 10% of the population. Okay, so I'll give you an example here, and your job will be to figure out which, if any, condition has been violated. Okay. So again, your conditions, so these are your answer choices. Okay, so A will be random independent violated. B will be large sample condition violated. And C will be big population violated. And D will be no conditions violated. Actually, okay, let me pull up Word. It's going to be faster if I type it. All right, so the my computer acting slow today. I hope it's okay. All right, so blank document. Let me just type in. Okay, so we'll say you wish to conduct a survey of UCLA students. Okay. All right, so you stand on Bruin Walk. Can I ask you a question? All right, and all right, and then so you. I'm glad some of you guys laughed. Okay, you survey 200 students who walk by. Okay, and we will say that 25 students answer yes to the question you ask. All right, so can you use the results of your survey for, I don't know. Okay, we'll do a statistical inference, meaning or are any conditions of the CLT violated? All right, so we'll take this. This is our thing. We'll run the survey here. Okay, and so go ahead and decide. You can talk to your neighbor, ask if you think any conditions here are violated or if everything looks okay.
Oh, wait, that's right.
Okay, we'll say just a few more seconds. Get your clicks in. Okay, just 10 seconds left. Get your clicks in. Okay, I think this is everybody here. All right, let's see. Okay, and the correct answer I'm going to say is the random and independent condition is violated here. Okay. All right. So the problem here is you survey students who walk by. Okay. So this is not a random sample. Because effectively, you're only going to survey students who walk on Bruin Walk, okay? Okay, so you only get students who walk past your location. And depending on the day you go there, okay, you might favor Tuesday, Thursday students or Monday, Wednesday, Friday students, or depending on the time you are there, okay, you might, that's going to affect the people who you might encounter. And it's also naturally going to favor those who go outside and walk, which, I guess depending on, what week we are in the quarter, there might not be as many people about. So this is not going to be a random sample, okay? Large sample condition, this is met, okay? So condition B is met. We have 25 yes, so we have 25 successes, and 200 minus 25, meaning 175 no's, okay? So, and both are greater than 10, so that that condition is met. And large sample condition is met, all right? Our sample is 200 students. Is there more than 10 times that many students at UCLA? Yes, right? So 200 times 10 is equal to 2,000, and the population of UCLA students is greater than 2,000. Much greater. Okay, and so, you know, the problem here is the fact that we are surveying those who walk by. So you have to be careful, all right? So random independent will be violated. You know, any kind of, you know, this is violated for any kind of convenience survey, convenience sample. Internet surveys will never be okay, you can't. Most people just click X when a survey pops up, right? You go to a website, they say, oh, or yeah, you're using an app. How do you like my app? No, okay? Go away, right? Internet surveys, those will not be random samples. And then even if you manage to send surveys to a random group, if only a certain number of people respond, if you don't get 100% response rate, then that's also not a random sample, okay? And then so samples with less than 100% response rate. So, I mean, you might manage to send surveys to a random group of people, but if only half of those people respond, then it's no longer a random sample, because now it's just those who felt like responding. And so that, you know, we got to watch out for the random and independent condition being violated. Okay, well, we'll end here for today, and we'll see you guys on Friday.